Hello class, and welcome to section 5.4, which is about transforming piecewise-defined functions. By the end of today's lesson, you will be able to analyze and graph the transformation of piecewise-defined functions. So we're going to start with the step functions. This one is much easier and it's very straightforward. So we're looking at a regular step function. In this case, it's the floor function. Same rules would apply to the ceiling function. It says f of x is equal to the floor of x. It's asking us to transform it up 4 units. So when I do this, all I'm going to have to say is g of x. We always change the letter out front so that we know that it's a different function, is going to equal the floor of x. And then we're adding 4 units onto the end. So it says whatever you have, get the answer, add 4 to it. So it's as simple as that. Go ahead and try the next one on your own. So our answer is going to be the floor minus 7 units. You might already have a step function that has been transformed a bit, and it wants us to transform it more. So in this case, I'm using the ceiling as an example. The exact same rules would apply to the to the floor. So now it says the ceiling of x plus 9, that's our original function. It wants us to go down 10 units. So from there, we need to subtract 10 units, giving me a -1. So my new function, g of x, is going to equal the ceiling of x, and then we're going to be subtracting 1. That's 10 units below where we started. Go ahead and try the second one on your own, moving this original f of x function up by 3. When I do that, I get g of x is equal to the ceiling of x plus 12. So if we're doing step functions, we're simply adding and subtracting. There's no stretching or compressing or anything reflecting like that. With step functions, it's just very basic transformations up and down around the graph. When we are looking at the absolute value functions, those give us more options as we are transforming. So my original function, f of x, is equal to the absolute value of x, can be transformed to g of x using these 3 different pieces. So we're going to go through what each of those mean. This h part inside the absolute value, that's directly connected to the x's, that's dealing with your lefts and your rights. So that's changing it. If you have x, for example, minus 3, that would mean you are moving 3 units to the right. So since we have the subtraction sign as part of the equation, when we plug in 3, it would just say x minus 3. If we moved it to the left, a -3, double negatives is what results in that positive h. So these inside the absolute value bar values, those move us left and right. If we jump to the outside of the absolute value bars, we have this plus k. If it is a negative k, so if there was a -5 on the end, that would mean the function is going down 5 units. If there was a positive 5 on the end, that would mean it's going up 5 units. Out front, this a tells us 2 things. First off, when you're looking at the stretch, you're looking at the absolute value of a. So even if the number out front was -1/2, when we're looking at the half part, we're ignoring the negative. So if you're deciding stretch or compression, you're ignoring any negative that might be there. If the value is greater than 1, so for example, there's a 3 in front of the function, it's stretching it out. It's making the function get taller. If it's between 0 and 1, so that goes back to that 1/2 example, if it's a fraction that's between 0 and 1, that's going to compress it. It's going to make it flatter. That last part with a is that if it is a negative, so if our value, and there shouldn't be absolute value bars there, so if our value is negative, below 0, so again, there should not have been absolute values around that a, I apologize. If our value is below 0, aka a negative number, it's a reflection across the x-axis. So it's saying you took your original absolute value function and flipped it upside down. So for example, if your a value was -1/2, that would mean you have a vertical compression and a reflection across the x-axis. So that a controls stretching and compressing as well as the reflections. So if we're looking at a few examples here, our first example says f of x is equal to the absolute value of x, and it's been transformed to say absolute value of x minus 7 plus 3. Right now we're simply identifying the transformation, so we're looking at which pieces are included. This -7 tells us that we are moving to the right 7, and then the plus 3 tells us that we are going up 3. So that's how the absolute value has been transformed. That's how it would look different on the graph. If we bump down to this second one, we got a lot more going on. So we're going to start out front with the negative. That negative implies that there is a reflection across the x-axis. You want to make sure you're specific on that because it is not a reflection on the y-axis, so reflection across the x-axis. This 1/2 part tells us that it is a vertical compression. It is getting smaller because 1/2 is between 0 and 1. Then this plus 8 tells me that I'm moving to the left 8 units, and the minus 10 tells me I'm going down 10 units. So each piece that was added on to the absolute value, the negative, the 1/2, the 8, and the 10, all of those tell us something about how the graph has moved. Go ahead and identify the transformation of this function on your own. We've got a vertical stretch because the 2 is bigger than 1, and then we're just going up 15 units because that plus 15 is outside of the absolute value bars. Last thing we're going to talk about is how to write a function if they have given us a graph. So our starting function, f of x, is equal to the absolute value of x. That would be the regular function that we saw back in the first lesson of this chapter that would have looked like this. Now obviously our red function has moved and we need to figure out how. The first thing that you are going to want to do is identify the vertex point. So where does it come to that point? In this case, our vertex is at -3, +4. So -3, +4. We're going to plug those values in for our h and for our k. So those tell us 2 of the pieces that we have. So as we are rewriting this function, that would mean we've got g of x is equal to the absolute value of x minus -3, which turns into +3, and then +4 outside of that absolute value for that k part. Now, the last thing we need to do is check if there is an a value. In this case, my graph has been flipped upside down, so I know that there is going to have to be an a value because that negative a is what flips it over. You always need to check to see if there is an a value. In order to do that, you need to pick any point from the graph. So for example, I'm going to go ahead and pick the point 0, -2. What I do then is I'm going to plug it in. So this is 0, -2. G of x is my output, so I'm going to say -2 is equal to, we're looking for the a value. So I'm just going to put an a there. And then I've got the absolute value of 0 plus 3 and then plus 4. So I've taken what I changed with my vertex, plugged in a point that I picked, and put a into the equation. Technically, I probably should have put a right here as well to say that I'm not done with the function solving yet. So now I'm going to go ahead and solve what I can. So 0 plus 3 is 3. The absolute value of 3 is 3. So that gives me -2 is equal to 3a plus 4. I'm going to go ahead and keep solving by subtracting 4 from both sides of that equation, giving me that negative 6 is equal to 3a. And I'm going to finish off by dividing by 3 on both sides, giving me an a value of negative 2. Now that is a good thing that we have a negative, because that is how our function flips upside down. So my final equation here, my actual answer for the graph is g of x is equal to my a value, which is negative 2, times the absolute value of x plus 3 plus 4. So again, quick recap of the steps. Find the vertex. That's what you're plugging in for h and k. Pick another point on the graph. Again, any point on this line would have worked. Plug it in to your function. Put the a value outside so that you can solve for it. Go through, find a, and then write out your final equation. Go ahead and try this one on your own. So that vertex point was at 4, 1. So I put in the x minus 4 and plus 1. The point that I picked out on my function was 5, 4. So the point that I picked out while I was solving was 5 and 4. Plugged those in for g of x and for x. When I did this, the absolute value of 5 minus 4 was 1. Absolute value of 1 is 1, giving me a. Subtracted 1 from both sides, giving me a is equal to 3. So my final answer for the equation was g of x is equal to 3, absolute value of x minus 4 plus 1. If you have questions about this or anything else from the lesson, please let me know when you get to class.